Hello, Project Lead the Way, Introduction to Engineering Students. This is going to be day one of a lesson that you can complete online. You're going to see that the instructions for the lesson are over here. It's always going to be in all capital letters. If you click on that, I give you the learning objective. And then in this case, there are two things for you to do. Both items must be completed for you to be marked as in attendance for the day. There are any of the information you'll need that I can put down here at the bottom, I will. And if you go back to the main page, both of those two things that were in the directions are right here. You should watch the PowerPoint presentation on Edpuzzle first, and then complete the assignment second. So this directions are just simply going to say go to Edpuzzle, log in and watch the video. You have to watch it all the way to the end in order for it to be recorded that you've watched it. Make sure you click the blue button at the end of the video. And for the assignment, open this up. You're going to do 1 through 4 in the assignment. The assignment and the handout are right here. They're also in the directions page that I already pointed out to you. You'll make a chart like this in your engineering notebook. Once you have the chart completed, take a picture of it and submit it. Submissions will show up here for me, and I will be able to grade those. We've done this type of work before, so it should not be new to you. So the PowerPoint presentation looks a little something like this. We're going to begin that PowerPoint presentation on tolerances, and this is what a tolerance is. It just simply means that the part itself can have variation to it. Typically, a part's going to never be the same. If you have two parts, there's always going to be flaws. There's always going to be things that are wrong with it. No two parts can be perfectly identical. So when you're talking about tolerance, obviously if the tolerance is too large, the quality of manufacturing goes down, and if it's too large, it might not even work in the assembly when you're done. If the tolerance is too small, that means that it's going to be very precise when you're making it. It's going to be very difficult to make that thing, and it's going to be really expensive. So there's a fine art to having a tolerance that's going to be the right size for whatever you're trying to make. We use the ANSI standards, and when we're using the ANSI standards, you'll see by the end of the week when we do some work in Inventor that we can add these types of tolerances to a part and what it looks like in Inventor. So I think I already said the definition of what a tolerance is, but it's the acceptable amount of variation you can have that still lets the part work appropriately. There are 3 different types of tolerances. One is called the limit dimension. It's right there. A second type of tolerance is called bilateral. Notice the plus and minus, and it's the same value. A third one is unilateral. Notice there's a plus and minus, but they're not the same. A limit dimension simply states point blank what the upper limit and lower limit is. There is no variation. There's no math that's required. Whatever the part is has to be between those two things. It's the limit. You can't be below this number, and you can't be above that number. A bilateral tolerance makes you do a little bit of math. The bilateral tolerance starts with a number, and then it tells you it could be plus that amount or minus that amount. So for example, it could be 0.250 plus 0.003 or 0.250 minus 0.003. The plus minus just simply lets you know how far it can be. So in other words, the range in that one is 0.006 because you can be above by 0.003 and below by 0.003. Unilateral, usually for a hole, simply means that the minus is usually 0, because if your hole is smaller than it's supposed to be, whatever you're trying to put in won't fit. So the plus means it could be larger than what it's supposed to be, but if it's too big, whatever you're trying to put in there might rattle around or it might not fit appropriately. So, but the hole, basically what we're saying is the hole cannot be smaller than that. There is 0 tolerance. That is the smallest value, but it could be a little bit bigger. So here are 3 types of tolerance. You're supposed to identify the 3-1. Give you a big hint. Each one, there's only 3, and there are only 3 here. So this one looks like unilateral because whatever this is has only one direction for its tolerance. This one looks like it's bilateral because of the plus and minus, so it can be in both directions. This is a limit. I have a lower limit and an upper limit. Kind of already mentioned this, but if this is the dimension, we would add 0.005 to that, and if this is the dimension, you would subtract 0.005 from it, and then you get what we refer to as the upper limit. And when you subtract the 0.005, you get what we refer to as the lower limit. So the range here is actually 0.1. From the upper limit to the lower limit, you get a range of 0.1. And there's your range right there. That's also referred to as your tolerance. The tolerance is actually 0.1. So when you're calculating the tolerance, you're saying that it should be here, and you can be anywhere in this range, and that would be acceptable. The tolerance is 0.01, the lower limit, and the upper limit. If you don't have a tolerance specified for a pipe, there's what we call general tolerances. And the general tolerances look like this. When you have a part that's dimensioned, if the part goes to only one place past the decimal, then this is the tolerance that you add. It's just like you don't have to put it in your dimensioned product because you just assume that the tolerance is going to be this amount right here. If the number that you're dimensioning goes to 2 places past the decimal, then we use this for the tolerance. If the dimensioned part goes to 3 places past the decimal, then we use this. So basically what we're saying is if you want to specify any other tolerance other than what's here, it has to be put into the part. Otherwise, when an engineer looks at a part diagram and they see that it's 1 place past the decimal, this is what we use for the tolerance on it. It doesn't have to be particularly stated, although sometimes they will put this as a general tolerance note down in the corner of a drawing page. Angles do have a general tolerance as well, 1/2 degree to either side. So you can see here, they did put a note. So this, since it goes to 2 places past the decimal, has this tolerance applied to it. This, since it goes 2 places past the decimal, has this general tolerance applied to it. Any of these other ones have it specifically stated. So this is a limit tolerance. This one over here is unidirectional. This one over here is bilateral. If a part doesn't fit within the tolerance range, it's said to be out of tolerance, and usually that part is rejected. It doesn't make it into the final assembly. Here are some other things related to tolerance. Again, 3 things. It's what we call a fit. So there's something called a clearance fit, and basically that just means that when one part has to fit into another, it's always going to have the clearance to be able to do that. There's something called an interference fit, which means when one part has to fit into another part, it'll never fit. In other words, they're not meant to go through each other. And then there's something called a transition fit, which could have a clearance and an interference at the same time. I'll show you examples of those right here. This is a clearance fit. The tolerance of this means that it will always fit into this spot. No matter what, even if this is the largest and this is the smallest, this will always fit. An interference fit means that when you have this part right here and this part right here, this part will never fit into that. It cannot go, even if you have the smallest number here and the largest number here, it won't fit in there. So what we call the maximum material condition is when the part that you're talking about has the largest amount of material possible. Okay, so the maximum material condition for an external feature is the upper limit. The maximum material feature for like a hole is the lower limit, because you're going to need more material if the hole is smaller. This one's hard to wrap your head around when you're first messing with these. So the least material condition means that you have the smallest amount of material. So the least material condition for an external feature is the lower limit. The least material condition for an internal feature, such as a hole, is the upper limit. Again, this is almost backwards, like you think of it as, because when you have a bigger hole, you're using less material in your part when you make it. So if you want to know what allowance is, so there's tolerance and then there's allowance, like how much will you actually allow. What you do is you take the maximum material condition for an internal feature and subtract from it the maximum material condition for the external feature. This is going to be something that you're going to do in the homework. This is why I'm making the PowerPoint available to you after this presentation, so you don't have to watch the video again. You can just simply open up the PowerPoint presentation and you can see how they're calculating allowance here. You take the maximum material for the internal feature. So the maximum for the internal feature, that's this number. You take the maximum material condition for the external feature, that's this number. Because if this one is 10, that's the biggest the part would be. And if this whole is 0.15, that is the most material you would ever use. So if you subtract those two numbers, you get 0.15. That's the allowance. So again, if you want to calculate allowance here, take the smallest number here and the biggest number here, subtract them. Notice that it's negative. Because it's negative, that means that this is an interference fit. More significant figures simply means greater tolerance. We're not dealing a lot with significant figures in this class. You will when you take chem. So there you go.